In the previous video, I gave a setup of a game that is an example of the tragedy of the commons. Now I want to discuss what will happen in this game, and we will also see why it is called a tragedy. As a quick reminder, we have n users or players which share a communication channel. Each user I picks a value xi between 0 and 1, and this value represents the amount of traffic that that user is trying to push through this communication channel. The payoff to user I is given by xi times 1 minus the sum over xj from j equals 1 to n. Or the payoff is 0, whichever value is greater. And each user is only interested in maximizing her own payoff. Now, let's say we are user I. What should we do in this game? So first we define ti as a sum of all the xj values except our own. So we sum up all the xj values for all the other users, and this is ti. So in other words, ti is just equal to the sum over all xj's minus our own value xi. If this value ti is at least 1, then the other users in the game already overload the communication channel, and so the payoff to user I, the payoff to us, is always 0, no matter what we do. So no matter what xi value we choose, we never get anything. So that's not very interesting, but if that is not the case, so if ti is smaller than 1, then our payoff will be xi times 1 minus sum over all xj's, which is equal to xi times 1 minus ti minus xi. And we would want to choose xi in such a way that this payoff is maximized. And this is an easy calculation, so you can do this on your own. You should just choose xi to be equal 1 minus ti divided by 2. That just maximizes this term. And of course, this is not just true for user I, but this is true for every user. We can apply the same reasoning to all the other users. The question now is whether there is a combination of choices of xi values for all users such that the system is stable, which means that no user would want to revise her choice, provided that all the other users also stick with their choice. And it turns out that there is only a single such state that does not overload the channel. So there's only a single state such that it's stable and the sum of all xi's is less than 1. And this unique stable state consists of each user I choosing xi equal to 1 over n plus 1. And I will leave it as an exercise to formally prove that this is indeed the unique stable state of this kind. This requires some arguments. But for now, let's just assume this is indeed the case. In this stable state, the payoff to each user is 1 over n plus 1, that's just the xi value the user chooses, times the quality of the channel, which will be 1 minus the sum of j equals 1 to n of 1 over n plus 1. So that's just equal 1 over n plus 1 times 1 minus n times 1 over n plus 1. And that's just equal 1 over n plus 1 times 1 over n plus 1. And that's just 1 over n plus 1 squared. Now this is the tragedy. Because if each user I had chosen instead xi equals 1 over 2n, the payoff for each user would have been 1 over 4n. This is easy to calculate. you can do this on your own. So every user would have gotten a much higher payoff, 1 over 4n instead of 1 over n plus 1 squared. So the payoff could have been by a factor of n plus 1 squared divided by 4n larger than the payoff we've actually gotten for each user. So this is more than n over 4 times as much. If n is large, so we have many users in the system, the payoff would have been much, much greater if we had chosen this other solution, which unfortunately is unstable. So why is the stable solution so bad? Why does this happen? This is a common phenomenon when the action of a player can bring large benefits to the player itself, but also introduce some additional cost to everybody. The benefit only goes to the acting player, while the cost is shared among many players. So for that reason, the large benefit to the player outweighs the share of the additional cost that the player incurs, because the overall cost is just distributed among many players. But if we look at the total cost introduced to the system by the action of the player, the negative impacts actually outweigh the benefits. So in this example specifically, making xi large is good for player I because she gets all the benefit, while the negative effect, in this case the degradation of the channel, is shared among all n users. User I is just not sufficiently penalized for hurting the other players in the game. Similar effects can be seen in many other settings, such as pollution, overfishing, or overuse of antibiotics, which then can result in antibiotic resistance. The term tragedy of the commons comes from a theoretical explanation of how overgrazing can happen when farmers share a common piece of land. So each farmer has an incentive to put a large number of cattle on the shared piece of land, because otherwise the cattle of the other farmers will just get a larger share of the grass. But the end result is that the land may be, at least temporarily, destroyed and become useless to all farmers. We will encounter and discuss similar types of tragedies and similar types of issues in a number of later videos.